homework 0 is posted on the website. If you didn't get an email and or don't have access to it and or whatever, talk to me after class. That one's due never, but you should do it soon. Correction, so in lecture last time I said a stationary space-time is one with a time-like killing vector. So that's what Wald says, that's an error. Well, sometimes people use this definition. It's not a good definition. The definition of stationary is that there's an asymptotically time-like killing vector. The meaning very far from everything, like large R. And here are some references for the first 2.5 lectures. So actually, I might write up some lecture notes for some of the stuff we're going to do later in the course. This is, right now we're talking about rotating black holes. This stuff is in lots of books. The chapter in Kerr is pretty good for an introduction. The chapter in Poisson is pretty good for a little more than that, especially if you want to know how to work out the pendulum diagrams that I'm going to do very sketchily later in lecture today. It's in there in detail for discussion of geodesics and the Penrose process and a really cool picture of something called the Dyson sphere, which I'll talk about today. You can look at MTW if you want to know some theorems as usual. Well, let's go.
So what is not called asymptotically stationary?
Well, if you're just looking at some patch, then we just delete this word and we say that there's a time-like killing vector. The reason we still call it stationary is just because it sort of matches with our intuition for things that are stationary. So like a rotating, like Kerr does not have a time-like killing vector.
You mean inside the right?
Inside the ergosphere. So even the exterior of Kerr. Okay, so we want to call that stationary because it's just an object that's spinning. So that's basically to avoid Kerr being not stationary. Okay, so I started talking about the ergosphere last time. We're looking at this rotating black hole from the top at a fixed time. It's spinning around this way. And the ergosphere, in this case, it's not spherically symmetric, so there's a loss of generality in drawing a picture like this. But I'm drawing is the equatorial plane of the space-time. So the ergosphere extends, so this is the horizon. The ergosphere extends some region outside of that, and we said that the boundary of the ergosphere is the point where the time translation killing vector becomes null. And so the time coordinate is sort of pointing straight forward in time if you're far away. The time coordinate starts getting bent over as you get close, and eventually it gets bent into the space-like direction. So outside the ergosphere, if I draw just the t in phi directions, the time coordinate, say the t vector does something like this, and inside it tips over and does something more like this. Now I'm drawing, well, I shouldn't have called that t. Let me not label it time, I'll just call it time. It's just a picture. Okay, so the evolution along the t direction takes you forward in time, but it's not time-like. It takes you to a new surface, which is separated from the old surface by going forward in time. But because you also went over here, you weren't following at a time like that. Now, the importance of the ergosphere. Questions so far? So this is where we stopped, basically. So remember that orbits, say, of a particle on the geodesic have a conserved energy, which is minus u dot zeta t. We can track the core velocity into that Killing vector. And outside the ergosphere, if you have some particle that's going forward, let me draw a particle and its light cone. So if you have a object, it has to travel on a time-like world line. Okay, so the fore velocity u is always somewhere in that light cone, pointing in the forward direction. If we're outside the ergosphere, then the zeta t Killing vector field is also somewhere inside the light cone. And that's why this minus sign is here to account for the fact that GTT is negative and ensures that E is greater than or equal to 0 when you're outside the ergosphere. Okay, because the time-like Killing vector is pointing forward, the fore velocity is pointing forward. That means that the inner product is negative, so E is positive. But inside, you have a situation where U, the fore velocity is still forward. You still have to be moving forward a time. But now zeta t is out here, and depending on the details of the kinematics, you can have either sign. So inside the ergosphere, orbits can have negative E. Because we're a little, so people say they have negative energy. This is accurate, but we have to be a little careful what we mean by energy. So let me make two comments. The first is that if we were to take one of these, so we're here, we can find the geodesics. If we were to take one of these geodesics and follow its whole path, its past and its future, one of these negative energy ones is always going to be something that looks like this. It sort of comes out and falls back in. It's never going to be a scattering. It's never going to be something that scatters the black hole or something that plunges into the black hole. And the reason for that is because what E is conserved is constant along a geodesic. So any geodesic that touches this region outside the ergosphere can't possibly have an E value that's negative for that geodesic, right? So, so the comment I wanted to write is that E less than zero orbits never leave ergosphere. The second comment is about what exactly we mean by E. Well, okay, second and third comment. So, the observed energy locally is still positive. What do I mean by that? I mean, you're flying on your rocket ship inside the ergosphere, and one of these negative energy particles, a rock or whatever, like knocks into you. You're going to experience, you're going to think that thing had positive energy, because the observed energy is minus u observer dot p object. I guess I've mixed dot u object. Okay, so if this could be a photon. I was phrasing it as if these were massive particles. It could be a photon. If you go in there with your photographic plate, your camera, and you measure the frequency of the photon, and that registers some energy on your photon detector, it's always going to be a positive energy, because that's this object, the observed energy that you're talking about there. Both of these things lie in the future light cone, and so have a negative there's a negative inner product, and that observed energy is always going to be positive. So what exactly is it? What is this thing called E? Well, the words people usually use are that E is energy as measured at infinity, because if you had a particle that could make it to infinity, it would be the thing you'd measure with your photographic plate. Now, this is tricky for things that can't possibly make it out to infinity, but we'll see how to interpret this a little bit later. Basically, the idea is this conserved thing E, it's still something you can talk about living far away, because you can throw stuff in, and then it can break apart and fall onto negative energy orbits. So we'll come back to that. Okay. Questions? Okay, so for the next little while, we're going to turn to some formal properties of the Kerr spacetime, and then we're going to come back to this phenomena, to the phenomena that you can get from the fact that you have negative energy. But we're going to start with the properties of the event horizon. So part of the goal here is to set up some concepts that, and some machinery that we're going to use later when we talk about general fluctuating horizons. At the moment, we're talking about the horizon, a perfectly stationary horizon of an equilibrium black hole. But I'm going to use some definitions and so on that'll be useful when we talk about black holes that, I don't know, you throw it, like as you drop something in, there's some lump on the black hole, that's it. So, talking about the event horizon, the first thing we need to do is write down the near horizon vector. So, if you look back at your notes from last time, you can see that the horizon is at what we call R plus, is m, the mass, plus the square root of m squared minus a squared. I'm not going to rewrite the metric because it takes too long, but remember that a is basically the angular momentum measured in units of mass. So the first thing, if you just try to, so one thing you could do is you could just take the line element of Kerr and you could just try to expand at r equals r plus epsilon. That's fine, that'll work. That's one way to get it where we're going here. But you're going to get a really messy answer. And the reason for that is because the horizon is rotating. So it's going to be much cleaner if we first go to a co-rotating frame. So the co-rotating frame, I'm going to denote by hats. So phi hat is phi minus omega ht. T hat is t. Okay, so I didn't really have to give that a new name, but you'll see why I wanted to do that anyway. Omega h here we defined last time. That's the angular velocity of the horizon, which for Kerr is equal to a over 2m plus. So this just goes into a rotating frame. Now I also want to zoom in on the horizon region, and the r coordinate is a little inconvenient for that because we have to expand your r plus. So we can make that a little easier by defining r equal to r plus times 1 plus rho squared. So rho now is going to be our radial coordinate, and the horizon is at rho equals 0. So if you take the line element that we had last time for Kerr, and you just do this coordinate transformation, so you just plug this in, and then you expand the row, then you get the following. ds squared is approximately some function of theta, f of theta, times minus rho squared d hat squared, plus a squared d rho squared, plus b squared theta squared, plus d of theta d phi squared. A and b here are constants that depend on little a and big M mass of the black hole. Did I mess something up? That should be phi hat. Okay, so I'm not going to write the functions. They're a pain. They're not going to be relevant for the discussion follows, and they would fill up the blackboard. So let's not write them, but you can easily find them just by doing this coordinate transformation and expanding in the horizon. Okay, so what do we want to notice here? First of all, well, really the most important thing to notice here is that this part of the metric is two-dimensional Rindler space. So Rindler space, as we talked about last semester, is just a piece of flat space. So this is a piece of flat R1, comma 1. Which piece is it? Well, if we draw a picture of the light cones in flat space, then Rindler space is this wedge region over here on the right. And basically what these t hat and rho Rindler coordinates look like in that wedge is t hat is evolution like this, and rho is the distance out that way. So rho is the radial coordinate in Rindler space, t is the time coordinate in this Rindler wedge. I'm going to give the coordinate transformation in a minute. That's looks like. Okay, so now we're ready to start talking about the Penrose diagram of the space-time. So far, we've only talked about the exterior of the black hole, so we're going to start just by drawing the outside patch. Before I do that, I want to remind you what is the Penrose diagram for Minkowski space. So R1, comma 1, two-dimensional Minkowski space. The Penrose diagram looks like this. This is infinity. This is future infinity, past infinity, past infinity. This is the origin of Minkowski space. And remember that the great thing about the Penrose diagrams is that they capture the causal structure of the space-time. So the Penrose diagram is obtained by conformally rescaling the metric so that it fits on your blackboard, but conformal rescalings don't affect the propagation of light rays, so they capture fully the causal structure, and light moves on 45-degree angles. So that's the reminder for Penrose diagrams. If we now go back to our Kerr black hole in the region R greater than R plus, well, actually, maybe first let's stare again at the R1 at the Minkowski space and just think about the Rindler wedge. So the Rindler wedge of Minkowski is obtained by sitting at the origin and sending out light cones to the right and left. So the Rindler piece is over here. Now, so what do we have? Now we can move on to Kerr. So for Kerr, if we're very far away from the Kerr black hole, then we're just doing flat space. So we know that the right side of the Penrose diagram is just going to look like this. This is just the flat space at infinity. And now from doing this coordinate transformation to the near horizon region, we know that we have something that looks like Rindler. So the conformal structure of the Rindler horizon is that it's this, it's these intersecting null lines. So for Kerr, we must have something similar. So this is this line here is like this piece of Rindler space. This line here is like that piece of Rindler space. So this one is called the future horizon, H plus, and this one is called the past horizon, H minus. The coordinates, these parts all correspond, both correspond to R equals infinity, and these horizons correspond to R equals R plus. So we saw some of this before, but I figured we probably forgot. So the things to remember are that the horizon is a null surface with this diagonal feature, that there's a past horizon and a future horizon that intersect at a point. Yes.
So the part of this diagram that you're suppressing is in a steady sphere.
That's right. Yeah, so let me talk about the extra parts. What I've actually drawn here is, say, theta equals pi over 2, and phi equals something. Okay, so what I've actually drawn is a two-dimensional picture, obviously. Now, if we want to think about the full space-time, then points out here represent S2s. Okay, so these are points out towards the asymptotically flat region. So I've drawn like the T and R directions, and so we drop the S2 parameterized by theta and phi. But points in here, well, points in here are still topologically an S2. I mean, there's still a closed two-dimensional surface corresponding to this point, which is parameterized by theta and phi, but it's not shaped like a sphere, okay, because there's no rotations. Same goes for points on the horizon. Points on the horizon are still topologically S2, although they're not geometrically. The metric on them is not the S2. The metric is this combination here, and take my word for it that G is not sine squared theta. It's something really awful. Okay, so so the metric on that horizon cross-section is something nasty. Other questions? Okay, now we're going to go slightly inside the black hole. Okay, so we know that in the near horizon region, it looks just like Rindler space. Now in Rindler space, of course, it's just flat space and funny coordinates. So you could certainly go past the horizon in Rindler space. It's not even really there. It's just completely made up. And there's nothing special about that horizon whatsoever. It's just an artifact of the coordinates. And that means that the same must be true of the Kerr horizon. So it is. And we can go slightly inside the horizon. By doing the usual Rindler coordinate transformation. So what does that look like? Well, we have a squared, rho squared, minus rho squared, dt hat squared. And the way to remember how the coordinate transformation works is to think of this as polar coordinates with an extra sign. So this is like polar coordinates on the plane, dr squared plus r squared d theta squared, except there's an extra sign here. So we know how to do coordinate transformation from polar and Cartesian. Well, first of all, we know what the answer is going to be. It's going to be Cartesian. But we also know how to do that coordinate transformation. It's just r cos theta and r sine theta with some extra i's stuck in to make everything make sense. So in this case, big Y here is rho cosh T over A. Big T is, sorry, that's T hat over A. Big T is rho sinh T hat over A. So anytime you see one of these polar coordinate-like metrics, you can just kind of mess around with the i's on your changed polar coordinates and get it to look like Minkowski space. So remember, we're doing the near horizon metric. We haven't written the exact Kerr metric here, so this is only good if we're pretty close to the event horizon. And this coordinate transformation, you can now use the big T and big Y coordinates over there. That'll get you a little bit past the Kerr horizon. There are much more complicated coordinate transformations you can do to get arbitrarily far. In other words, you can do something very similar on the full Kerr, on the full Boyer-Lindquist coordinates that we started with. That's like going to Kruskal coordinates. We did it for Schwarzschild last semester. We're not going to bother. We can already see from here that clearly these horizon pieces that we drew here, we can go past them, and at least locally, it must look pretty much like the case in Rindler, so we know there's some kind of X here with additional regions beyond the Kerr horizon. Okay, so we did talk about some of this stuff last semester. I'm not sure if I'm losing people because it's boring, we already did it, or losing people because we totally forgot what we did, but stop me with questions if it's the second one. Throw tomatoes if it's the first one. Good. I'm going to talk about something a little new. This is going to seem sort of trivial in this example, but it's something that we're going to deal with in great generality maybe next week or a week or two. So I want to explain how this works for Kerr in this example where we have a nice explicit metric. That's the idea of the horizon generators. Okay, so the definition of the horizon generators is that these are null geodesics on the horizon. What does that mean? Well, okay, we have to think of the event horizon as this whole line here. It's not just, it doesn't exist just at one point in time, it's this whole surface in space-time. And you can tell from looking at it that it's a null surface because it's going at 45 degrees here. And what we want to look at are null geodesics that sit entirely within this entirely at r equals r plus, either on the past horizon or on the future horizon. So let's start with the case of Rindler space. In Rindler space, we have the t-coordinate and the y-coordinate. So what are the generators? I'm going to save this for later, so I'm just going to put it in the bubble and we're going to ignore it. So what are the generators of the Rindler horizon? That's a question.
T plus minus y.
T equals plus minus y. In other words, I'm telling you what the shape of the curve is. There's various ways that you could say it. I'm telling you the equation for this line and that line. And those are both obviously geodesics. They're straight lines in flat Cassie space. In Rindler coordinates, these are rho equals 0, t hat equals anything. So the curve, in other words, this tells you about the curve. I pulled sort of a fast one here. This is a common thing to do, which is that we're trying to talk about the horizon. And in these rho t hat coordinates, remember rho was going this way, t hat was going that way. The rho t hat coordinates do not include the horizon. So rho equals 0 is a bad coordinate singularity. We're not supposed to talk about it. But here I am talking about the horizon in rho t hat coordinates. Anytime I say something like this, what you have to imagine is that what I really mean is that you take a limit if rho goes to 0, and that secretly we should be thinking about the generators in a smooth coordinate system that goes past the horizon. But it's still handy to think about it this way, so we're going to often do that. Okay, so for Kerr, the generators, well, we can just borrow this Rindler result because in the vicinity of the horizon is just Rindler space times some extra stuff. So the generators are R equals R naught. Sorry, R equals R plus. Let me come back to that. Theta equals theta naught. Phi hat equals phi hat naught. And t hat equals anything. In other words, if you take, so this has to be understood in the sense of a limit, like here. So rho and r were related by some simple scaling. So in the same sense as here, we could talk about the horizon as being at rho equals 0. but we're sort of cheating because of the coordinate singularity. Same is true here. You can think of the horizon as being at r equals r plus, and then you can think of t hat as a coordinate along the horizon. But you have to imagine doing the coordinate change to t and y if you actually want to use this smoothly. So in the limit rho goes to 0, the point is that t hat becomes a coordinate that measures how far along you are along this null surface or along this null surface. Okay. If we actually draw this on the Kerr horizon, so let me try to draw in the, I'm just going to draw in t phi Boyer-Lindquist coordinates. So in Boyer-Lindquist coordinates, a curve parameterized by t hat, which sits at constant phi hat. So sitting at constant phi hat means that you're co-rotating, right? Because constant phi hat means that as you go forward in t, you also go around in phi. So these generators of the horizon sort of look like these null lines that sort of go around the cylinder. Like this, they go. So there are some generators on the horizon. They're labeled. The ones that I'm drawing here are labeled by different values of phi hat naught. I've suppressed this direction, and where you are along the curve is t hat. So t hat is a coordinate along each of these curves. Usually we don't have to worry about the curves themselves, and we just talk about their tangent vectors. We know the tangent. We know the vector field, which is tangent to these curves. That's sort of good enough to know everything there is to know about the curves. So what's the tangent vector here? U alpha is dx alpha d lambda, where lambda is some parameter along the curve. So the only coordinate here that's changing as we go along the curve is t hat. So this is just, we could just take to be a vector pointing in the t hat direction. This is now why I gave t hat a hat. Okay, so this is always confusing. When you shift phi, make sure I got this right. When you if you do a coordinate transformation that shifts phi by t, then if you now go to partial derivatives, it's the dt that shifts versus dt hat. Okay, so ddt is not equal to ddt hat. That's why I gave it a different name, because when we take a partial derivative in the hat coordinates, we take that at fixed phi hat. So that's what that hat means. That's why we have to be careful to put that there. So dt hat in the original coordinates is dt plus omega h d phi. That's just the usual coordinate change for vector, for derivative. So let me call this thing zeta h. So zeta h is the vector field of dt plus omega h d phi. And this is the tangent vector along the generators of the horizon.
fixing phi hat, drawing t, you are compared between t prime and rho or r.
Which
in the
drawing
Penrose
was that?
diagram.
Oh, the Penrose diagram.
So you're fixing phi.
Doesn't make a difference. I don't think.
Because it doesn't depend on phi.
Yeah. Other questions? Okay, so I kind of argued that this was the generator. If now you want to go and check it, you want to be really sure, then let's be a little bit more careful. I'm just going to write sort of what you would do, and I'll probably put this on the homework. So first of all, you should check that it's null on the horizon, so that this zeta h goes to 0 as r goes to r plus. That's easy enough to check. You just literally calculate the norm, and then you evaluate that norm as you take r. In the original Boyer-Lindquist coordinates, we have it here in Boyer-Lindquist coordinates, and then you just take it to 0. That's the first check. It works. I should add some terminology here. So this is called a killing horizon. The null surface, if you have a null surface that corresponds to a killing vector having 0 norm, then that's called a killing horizon. So the Kerr horizon is a killing horizon. It's not true in general. You can have killing horizons that are not black hole event horizons. You can have event horizons that are not killing horizons. So for example, the Rindler horizon is also a killing horizon. It's a killing horizon for the boost vector, for the boost isometry of Minkowski space, but there's no black hole. So there's lots of different kinds of horizons, and we're going to talk about various ones. In this case, they happen to coincide: killing horizon and event horizon. The other thing that you should check to be sure that this is really the generator is the geodesic equation. This is a little trickier. So let me tell you what happens if you do this calculation. So what is the geodesic equation? Well, usually the geodesic equation is u alpha grad alpha u beta equals 0. But if you actually go and calculate that for this zeta vector, that's not what you get. You get some number kappa times zeta beta. The reason for that is because the geodesic equation is only going to look like this if you have an affine parameter. Okay, so this is probably, if I'm sure I mentioned this in the first semester, but then we promptly forgot about it, and we never talked about non-affinely parameterized geodesics ever again. But this is a case where it's useful to parameterize things in terms of something that's not affine. So this t hat coordinate that we've been talking about, that measures how far you are along the horizon, is not an affine parameter along the null geodesic. So even though it is a geodesic, it does not obey the usual geodesic equation. It has this other form. You can check. Okay, so t hat is not an affine parameter along this curve, but there exists a scalar function f so that zeta h tilde, which is f zeta h, obeys affine geodesic equation, zeta tilde h, alpha, grad alpha, zeta tilde h. So I just wrote the geodesic equation again, this time it's equal to 0. So what's happening here is that the geodesic equation, if we're talking about time-like geodesics, then the geodesic equation in this nice form is true if you parameterize the curve by the proper time. It's not true if you use some other random function to parameterize your curve. On null geodesics, we don't have the option of using proper time, but there's this similar issue with whether or not it's affinely parameterized. So affine, by definition, an affine parameter is one with a tangent of this equation, and it just amounts to changing where we put these tick marks in how we define our distance along the curve. Yeah.
For calculating this equation, was there a way to see that t hat was not affine, or is this supposed to be like a definition of something that is not parameterized?
I think it's just the definition. I think of it as the definition. I can't think of a more primitive definition. I think it's just the definition. So I think I'm going to put this on the homework. This is actually it's a little tricky to calculate this. So if you try to calculate this, in Boyer-Lindquist coordinates, you will get into trouble, and you'll find 0 on the right hand side. But that's because we're trying to evaluate this at the horizon, and if you ever get into trouble evaluating things at the horizon in Boyer-Lindquist coordinates, the easiest thing to do is to do this Ringler type coordinate transformation that we were just talking about. So you go to the co-rotating frame, you have ddt hat, and then you do so you have to do this coordinate transformation in order to even make sense of what the terms in this equation mean, so that you can evaluate it at the horizon. And that's generally true when you actually want to evaluate these vector fields. You have to make sure you use coordinates that are smooth there.
So is K somehow related to the surface gravity in this case?
Yeah, it actually is the surface gravity.
And you're saying that that's coordinate dependent?
No, it's not. So, this zeta that we've picked is normalized so that the ddt piece is 1 out near infinity. I mean, when I wrote this vector field, zeta h, I wrote it with a particular normalization, and if you write it with this particular normalization, so that there's a 1 here, then that defines what's called the surface gravity. I'm not sure if I'll talk about it, but it's called kappa, and there's no normalization freedom here. It's built into the fact that we've normalized zeta that way. Does that make sense?
But I think you said that the right hand side vanishes if you choose some other coordinates.
If you reparameterize the horizon, you can make the right hand side vanish. So if you reparameterize t by multiplying it in such a way that multiplies the vector field by this function f, then zeta tilde kills the right hand side. But the thing that's called the surface gravity is the thing that shows up for this particular zeta, not some other rescaled zeta. more terminology. The bifurcation sphere. Okay, so anytime you have a killing horizon, you have a bifurcation sphere. Here we have a killing horizon. So the bifurcation sphere is easiest to define with a picture. Okay, so here. When you have a horizon and you draw one of these x's, the bifurcation sphere is that point, or the bifurcation surface in general is that point in the middle of the x. For Kerr, this is a sphere because, well, it's topologically a sphere because we have the theta and phi directions that are being suppressed in these pictures. So that's like the horizon. It's the horizon at sort of time 0, roughly speaking, but t is not a good coordinate. Okay, so we have to be careful what we mean by that. But this is bifurcation sphere. Let me give a better definition. So the definition is the locus with ZH equals 0. Notice I'm not saying whether it's null. I'm saying it's literally 0. Okay, so the horizon, this whole horizon here, the generator zeta h is going to be null, but at that point in the middle, it's not just null, it's literally the vector 0. Okay, and you can see that it has to be the vector 0 because along here, it's a vector that's pointing this way. Along here, it's a vector that's pointing that way. So the only way that you can smoothly get from a vector that's pointing this way, one that's pointing that way, is if you're 0 at the middle. Okay, so if we talk about this in, this is easiest to write in Rindler. So in Rindler language, this is the big T direction. This is the big Y direction. The generator of that horizon is the boost vector, which is y dt plus t dy. So if you look at that vector along here, it's going to be proportional to 1, 1 in ty coordinates. If you look at it down here, it's going to be proportional to 1 minus 1. But at the bifurcation point, you set y equals t equals 0. So that the horizon vector zeta h is just literally the vector 0, 0. I'm going to draw the Penrose diagram. Decided not to dwell on this Penrose diagram just because it's really messy, and we're going to have lots of opportunity to do Penrose diagrams later in cases where it's a little easier to follow. So I'm just going to draw it because it's really fun. So what do we have so far? So far we derived the outer Penrose diagram. Okay, so this is where we live. There's a star plus and a star minus here. There's the horizon, R, which is R equals R plus. This is R equals infinity. And we know from our Ringler coordinate transformation that at least it keeps going for a while on the other side. In order to get the whole Penrose diagram, it's a really messy, annoying process where you have to sort of follow the coordinates through this way, and then you have to follow them. Well, you can find global coordinates on this piece, but okay, I'll draw it and then I'll describe. Okay, so it just keeps going like this infinitely many times in the past and future. So what's happening here, there's our patch, which is asymptotically flat out here. There's this x corresponding to the horizon. Everywhere along this x is r equal r plus. There's a second infinity. Did I do something wrong?
What is this region? Is really removed?
No, I'll come to that. No, they're really there. Okay, so there's this wormhole, just like in Schwarzschild. On the other side of the wormhole, there's a second infinity, flat infinity, which has a new scri plus, new scri minus. We can't actually get there, just as in Schwarzschild. It's causally, you can tell just from the Penrose diagram that it's causally disconnected from us. So if you fall in, you're going that way. You're never going to get to the other side of the wormhole. But now, let's see. Okay, so now you're going to find another horizon because Kerr has, remember there was two horizons for the Kerr space-time. So that one is r equals r minus. And that gives you this second x here. It's all at r equals r minus. This squiggle here is the singularity. And for Kerr, actually, the singularity is not a point, it's a ring. So this is explained in Carroll. I'm not really going to go into it. But basically well, it's a ring. Okay, I'm not going to say much on that. But there's a singularity that's in space is shaped like a ring. So at a given point in time, there's a singularity shaped like a ring, and that means that you can go past the singularity and come out the other side of the ring, and that's this region. So this is another flat region on the other side of the ring singularity. Actually, I don't think this region is good for anything. It has closed time-like curves. And probably doesn't really make much sense for anything. But if you take the metric seriously, then that's what you find. There's this ring, and you can come out the other side. Or if you're lucky, maybe you can fire your rocket booster or something and head up this way and come out into a new asymptotically flat region where you can live happily ever after. What else do I want to say about this? This region here, or these lines here, at r equals r minus, are called the Cauchy horizon. And I don't think we should take this diagram seriously past the Cauchy horizon. Basically, if you look at anything the least bit realistic, even, well, some people would say we shouldn't really take this seriously because it doesn't exist in collapsing black holes. Even if you're willing to take this seriously, you should not take anything past here seriously because perturbation, any kind of perturbations that you add will totally
destroy a Cauchy horizon. Furthermore, you don't know how to do physics here because there's a singularity in your past. And what do? Physics, we take data and we follow equations forward in time. Well, if you have a singularity in your past, you don't know how to do that. Okay, so we really don't know how to make sense of physics in this reason. So, but it's fun to draw the whole diagram. Questions?
So just about that region, how do you know that you're going to somewhere else? I mean, shouldn't you pass R minus R plus at some time? I
Say
mean,
that again?
in the region that you drew,
Yeah, up here?
no, the region that you have close time numbers.
Oh, this one?
Yeah.
Uh-huh.
So, how do you know that you're gonna head towards some other regions? I
You mean out here or?
yeah, I mean, shouldn't you pass R minus R plus at some point?
Again?
Yeah.
No, this is all happening at R, this is all negative R. And the metric doesn't, the GTT or this function delta of R, whose roots were the horizons, has no roots at negative R. So there are no horizons over here. Delta of R is R minus R plus, R minus R minus, up to a constant. So it only has positive roots, and if you lived here, you would think that you lived in a naked singularity with closed time-like curves, basically. I don't think it's.
The metric is real, yeah. Still.
It's
R negative.
Yeah, the metric is real. Yeah.
Why does the fact that the ring singularity mean that you can avoid the singularity?
Well, if your singularity is at, so for Schwarzschild, the singularity is at R equals 0, and there's no way to get past the point R equals 0. Okay, you can head towards R equals 0, you can hit it, but now you're done. There's no past. Okay, for Kerr, if you look back at the coordinates that we used last time, the singularity was at this thing equals 0, which is R equals 0 and theta equals pi over 2. So it sort of only exists at a certain, and now, okay, now we have to do various coordinate transformations to figure out what this looks like. But it turns out that this locus is a ring. It's not a point. You can do some coordinate transformations and find it. Yeah.
You don't necessarily have to. You don't like in principle. If the metric was perfect, you could just keep going forever, right? You don't have to hit a singularity in this.
That's right.
space.
That's right.
Is that different than the statement that because the singularity is a ring, you don't have to hit it?
Yeah, it's
You're
different than
saying
that
something
because
different.
in Reese and Nordstrom, the Penrose diagram is identical, but we would delete this, and there's no ring singularity in that case at this point. So it's different. It's going through this way versus heading out that way. Okay, so we're going to have lots more to say about generators in a week or so. But for now, I want to go back and talk about this negative energy business again. The basic way to understand why this is important extracting energy from rotating black holes. So let me first just sort of draw a picture and tell you how this works. So here's your rotating black hole. Here's your ergosphere. And here's somebody far away from the black hole who would like to, I don't know, get a lot of energy out. They want to build a power plant. Okay, so what can they do? They can't immediately extract energy from the black hole because then well, what the strategy is going to be to throw negative energy stuff into the black hole. Remember we said that the stuff can have negative energy in the ergosphere. So we're going to try to throw in negative energy stuff, and that's going to give us energy out. Okay, so how do we throw in negative energy stuff? We already said that people out here you can't have a negative energy particle out here. But that's okay, because what you can do is you can throw in a particle with positive energy. So E, energy E, and say a piece of garbage or whatever on a spaceship. And that spaceship can be pre-programmed to eject out some garbage while it's in the ergosphere. Okay, so you throw in a spaceship carrying your garbage, and when it gets to here, it throws that garbage onto a negative energy orbit. So at this point here, your spaceship throws some junk on an orbit with E1 less than 0, and the spaceship is going to be deflected because it's throwing some stuff in. Conservation of form momentum at the intersection point here tells you, okay, so let me call this P1, P2. So conservation form momentum is going to be conserved at this point here. P is equal to P1 plus P2 at the ejection, which means that E is equal to E1 plus E2. And we threw in this junk on one of these negative energy orbits, which means that our spaceship is going to be returning with energy E2, which is greater than the energy that it had when it started to fall in. So the spaceship falls in, ejects the negative energy stuff into the black hole, heads back out, and now has more energy than it started. Energy is still conserved, where this energy didn't come out of nowhere. It was extracted from the energy of the black hole itself. So the total energy in space-time has to be conserved, but we had the energy in the black hole, and we just transferred some of it to our spaceship. So we extract energy while in the process decreasing the mass of the black hole by throwing in this negative energy stuff. This, yeah.
In a space-time with two Killing vectors, you have form momentum being conserved as a vector of a four vector?
What I mean by conserved is that, no, so P, this 4 vector, is not conserved along the geodesic. It's not conserved in that sense, because we only have 2 Killing vectors, not 4. But at the point where you at this interaction point here, if you evaluate P P1 and P2, we can locally just do special relativity. So within this little interaction point here, it's true that instantaneously P is equal to P1 plus P2. Now, each of those four vectors is not going to be conserved along the ensuing paths, but it's true that at the ejection point, P is equal to P1 plus P2. And now, the full four vector is not conserved as it comes back out, but the energy is because of the energy, because of the ddt. Okay, so this is an enormous amount of energy. The amount of rest energy in the supermassive black hole at the center of our galaxy, I checked yesterday, is 10 to the 36 joules. Okay, this is ridiculous. And you can kind of work through this process and find that the amount of energy that you can extract here is some fraction of the rest energy of the stuff that you threw in. So if you throw in some trash, then your spaceship can return with energy that's sort of order fractions of the rest mass of the stuff you threw in. So you can convert garbage into rest mass energy. And this sounds pretty contrived because we had this spaceship going in the black hole and it was ejecting some garbage. Actually, it's not nearly as contrived as it sounds. Let me see if I have time. No, I guess I'll come to this next time, but for now, I'll just say that there's a wave version of this. So, or basically waves and more complicated stuff like electromagnetic waves, plasma, etc. There's an analogous process whereby that stuff can extract energy from a rotating black hole. So it is, to some extent, believed that some version of this phenomenon is responsible for some of the most energetic astrophysics that we see in the sky. So like rotating black holes have this enormous energy release in jets. And not literally, okay, it's not literally this thing where a particle breaks into two particles, one falls in, one comes out, but a sort of analogous process happens in plasma that allows the plasma to extract energy from the rotating black hole. We don't understand jets very well, but it's believed to be one of the engines powering that massive energy release. So this is something that's really important in the sky and really does happen roughly speaking. So I will stop there for today.